So our goal in this lesson is to learn how to relatively quickly find roots of complex numbers, so square roots, cube roots, fifth roots, and then apply that in solving equations. So before we get started, let's take a deep breath. And let's begin. In this first example, I'm going to walk us through how to solve the equation z cubed equals 8, giving your answers in the form x plus iy. So you might have noticed that the title for this lesson is Roots of Complex Numbers. And you'll notice that what I'm working with here is actually a real number. I decided that I'd start with something real because this might be a problem that in some sense we already know how to do, but we may realize we don't actually. If I were to just take the cube root of both sides of this, if I were just to do z cubed equals 8 and cube root both sides, we get that z is 2, which is good, but you may remember from earlier in this unit, the fundamental theorem of algebra tells us this is supposed to have 3 solutions. There are supposed to be 2 other ones, and it might be that this is a triple solution, but it turns out there are actually 2 other complex solutions. And so I want to go through the method for how we're going to do this. The next thing I'll do is I'll sort of write out for you what all those steps are. So in this first one, you can sort of follow along and write down any questions or concerns that you have along the way, and hopefully I'll address those over time. So the first thing that we're going to do is we're going to take the thing that I want to root, and I want to write that in polar form. Okay, so fortunately 8 is fairly easy to write in polar form. If you think about that in an Argand diagram, 8 is just over this way. This is our real axis, this is our imaginary axis, and so if you've got, 8 on the real axis here, then I can write that z cubed equals 8 cis 0. Just to make sure everybody understands that. So the 8 here is representing the fact that the complex number that I'm wanting to root has a magnitude or a modulus of 8. And the 0 is representing that the angle this makes with the positive real axis is 0. It's like up 0 off of that. Now, this next step is not confusing, but it's very important and we can't forget it, right? I'm supposed to be winding up with 3 solutions to this, and right now I'm still only working toward 1, and it's at this step right here that we see the other ones. This angle doesn't have to be 0. It could also have been all the way around the unit circle. I could say that this is z cubed equals 8 cis 2 pi. I could also say that it's not just 2 pi, but 4 pi. So I could also have z cubed equals 8 cis 4 pi. Now, in theory, I could actually keep saying 6 pi, 8 pi, 10 pi, 12 pi. I'm going to leave that out for now. I'll come back and talk about it in a moment. Now that I've got all these things, I'm going to solve all of them the same way. Okay? With all of them, I'm going to raise them to the 1/3 power. I'm going to work it out for this first one, and then I'll bring this reasoning to the other ones. When I raise this to the 1/3 power, I suppose really what I'm doing is I'm raising each side to the 1/3 power. When I raise each side to the 1/3 power, on the left, z cubed to the 1/3, that's just going to be z. On the right, de Moivre's theorem says that I can take this power and apply it a little bit differently to each of these things. I'm going to raise 8 to the 1/3 power, and then I'm going to multiply the argument by that. Remember, that's what de Moivre's theorem told us. So that means that z is going to be the cube root of 8 is 2, so 2 cis 0. So this is one of my cube roots, and I'll convert that to x plus y. And let's actually do that right now. So to convert this into x plus iy, we just need to do 2 cosine 0 plus I sine 0. So that's 2 times the cosine of 0 is 1, the sine of 0 is 0. So I got z equals 2. So this is one of my 3 cube roots of 8, which you'll notice is actually the one that we literally already knew about. So these other 2 things must be the ones that are going to find those other hard-to-find cube roots of 8. So I'm now going to follow the exact same process, the exact same things I did here, I'm going to do to these 2 things. So first, we raise both sides of this to the 1/3 power. Doing that gets me z on the left. On the right, it's going to get me 8 to the 1/3 cis, and then I multiply that 1/3 times the argument that's inside. This gets me z equals 2 cis 2 pi over 3. And then I can expand this out to find out what it really is. Cosine 2 pi over 3 plus I sine 2 pi over 3. So this is 2 times, now the cosine of 2 pi over 3. 2 pi over 3 is like up this way. So cosine is small and negative, and sine is large and positive. So this is going to be negative a half plus I root 3 over 2. And then when I multiply that 2 in, I get negative 1 plus I root 3. So this is my second cube root of 8. Go ahead and pause the video and work through this other one on your own. So for this one, if I raise both sides to the 1/3 power, I'm going to get z equals 2 cis 4 pi over 3. Just multiplying that in. So if I expand this, this is 2 cosine of 4 pi over 3 plus I sine 4 pi over 3. And if we again think about the unit circle value, which would be down here, it's still negative a half here, but it's negative root 3 over 2 here. So here I have negative 1 minus I root 3. Neat observation here. You remember from before that when you have a real polynomial, you always end up with conjugate roots. We're seeing it right there. Now, I know in this lesson I said that I was going to be solving these relatively quickly, and that was 6 minutes. This is still sort of a complex process, but as we do it more and more, our speed does increase, and I think you'll find as we do more examples of this, it doesn't really get more complicated when this is something that's not real. Once you've figured out what the starting point is, you're just following a process as you go through these. As promised, I will now provide or sort of go through what that formal process is. And we just saw it, but what that process is first, if necessary, you isolate the Zn. So if you have something like z to the nth power plus 1 equals 3i, your first step needs to be to move that over, to get it to be z to the n equals negative 1 plus 3i. We'll see an example of that later, but just make sure that you've got that alone. Your next step is to take this number over here and write it in polar form. So whether that's something you do with a calculator or without a calculator, you want to write that in the form r cis theta. Okay. Now remember, when you do that, you need to write multiple versions of that by adding 2 pi so that you'll wind up with n solutions. So if your first one was, let's say 4 cis 1, you would also want to write 4 cis 1 plus 2 pi. And 4 cis 1 plus 4 pi. And you're going to keep adding on 2 pi until you have, n different versions of this thing. Okay? Your next step is that you raise both sides of the thing to the 1 over n power. So if all these things were equal to z to the n, you'd raise both of these things to the 1 over n. Z to the n. So you raise both sides to the 1 over n. Step 4, you simplify the right-hand side by using de Moivre's theorem. So you're going to take this and make it the power of this, so 4 to the 1/4 power, and you multiply inside with this argument. Okay? And then, I didn't write it in here, but you after you've done that, you then simplify each. So if possible, do the 4th root of this, work out what this thing is. And then step 5, if the problem asks you to, you would then take this and convert it into Cartesian form. In the examples we're going to do today, some of them will ask you to do that and some of them won't. So this is the process that we just used. We're now going to use that and apply this process to 3 different examples, and each one is going to get a little bit more difficult. So each time I want you to be looking for opportunities to learn and understand this and to practice your skills. Now that you've seen formally what this process should be, I'd encourage you to pause the video and try this one on your own. If you feel a little unsure, remember you can always sort of watch the beginning of it and then try some of it on your own. So step 0 was, make sure that we've isolated our z to the n. In this case, this is isolated. Our next step then was to write this in polar form. All right, so we'll take a moment here to think about this on an Argand diagram. Argand diagram is going to have this, to the right 8, and then up 8 root 3, which is sort of even more. So this angle is going to be up here, and this feels like a unit circle-ish value. So, we might take a moment to figure out what the argument is. Our argument would be, so the argument of this, I guess I didn't need to write that. The argument for this would be the arctangent of the imaginary part 8 root 3 over 8. That's the arctangent of root 3. And sure enough, that is one of our unit circle values. This is pi over 3. Great, so we've got that. The other thing we need is the modulus. 8 plus I 8 root 3. The modulus of that would be 8 squared plus 8 root 3 squared. That's 64 plus 64 times 3, which is 192. That's going to be the square root of 256, which is 16. Okay, great. So now we've got our modulus, we've got our argument, we now sort of bring them back to the problem, right? We can now say that z to the 4th is 16 cis pi over 3, okay? But remember, this is a 4th power thing, which means there really should be 4 versions of this. So I'm going to have, this one, 16 cis pi over 3. My next one is going to be z to the 4th is 16 cis, and then I need to do pi over 3 plus 2 pi. So plus 6 pi over 3. So this will be 7 pi over 3. I also need to have z to the 4th, which is going to be 16 cis. I could add another 2 pi over 3, another 6 pi over 3. That would be 13 pi over 3. And since there are 4, I could actually do it again. I could do z to the 4th is 16 cis. Now this one plus 6 pi over 3. That's going to be 19 pi over 3. Great, so now I've sort of got my setup. I've got my space for all 4 of these solutions. I'm now going to do the 4th root of both sides of this one. I'm actually going to do the 4th root of all of them, but I'll do them one at a time. The 4th root of this is going to get me z, and we might call it like z1 because we're going to find like our first solution. z1 will be 16 to the 1/4 power cis, and then it's going to be 1/4 times pi over 3. So z1 is the 4th root of 16, which is 2. So 2 cis pi over 12. Now you notice this problem didn't say anything about the form that my answers need to be in, which means this is good. I mean, you like, yay, I found it, right? So 2 cis pi over 12. We can go over to the blue one now. I'm going to do the same thing. I'm going to raise both of these to the 1/4 power. Okay. On the left, I'll have z. On the right, I'll have the 4th root of 16 cis 7 pi over 3 times 1/4. Maybe I'll call this z2 now. The 4th root of 16 is still 2, and then this is going to be cis 7 pi over 12. And you may have noticed these computations are kind of getting repetitive. I think it's worth noting that particularly if you've shown your work well for 1 or 2 of these, it's okay for you to sort of move quickly through these other ones. Just take care not to make any mistakes. I'm going to raise both sides of this to the 1/4 power. When I do that, I'll get z equals, we know what's going to happen here. This is going to come down and give me 2 here, cis 13 pi over 12. So there was z3. And then finally z4, same deal. I would do 4th root on both sides of this. This is going to get me z4 equals 2 cis 19 pi over 12. So there we go. This one only took us 5 minutes, and it was a 4th root. There was sort of even more work to be done on this one. Now, I do want to point out something interesting really quickly on the Argand diagram for these. if you were to take these and plot them on an Argand diagram, and I'm not going to ask us to convert them, but if I took these and plotted them on an Argand, I know these aren't unit circle values, but where is pi over 12? Pi over 12, like if this is pi, and this is half of pi, and this is a quarter of pi, and this is like a pi over 6, pi over 12 is like here, right? So 2 cis pi over 12, 2 cis pi over 12 would be like here out to a length of 2. Where is 2 cis 7 pi over 12? 7 pi over 12 would be like just a little bit past pi over 2. This would be 2 cis 7 pi over 12. What about 2 cis 13 pi over 12? 13 pi over 12 should just be a little bit past 12 pi over 12, which is 12. Which is pi. So this would be 13 pi over 12. Do you see what I'm going to be getting at here? 2 cis 19 pi over 12? 19 pi over 12. That's just a little bit past 18 pi over 12, which is 3 pi over 2. This one is right here. What you're going to find when you're doing these roots is that these roots are always evenly spaced around a unit circle, or I guess in this case like a 2-unit circle. All these are supposed to have a length of 2, and they should be sort of spaced out around this thing. It's just a really, really neat observation that you'll see as you work through these problems more. We've got another example here that's going to be really similar to the last one. This one does have the 0th step, so we'll get a chance to see that. If you haven't tried one of these on your own, make sure that you sort of pause the video and give yourself a chance to try the beginning of this. So first step, as we know, is that we need to move this 32i over to the other side. So we'll have z to the 5th power equals positive 32i. Next step then is to take the thing on the right and convert it into polar form. So you think about the Argand diagram, you think about where positive 32i is, that's straight up, which means that we're going to be able to write this thing as 32, the modulus, cis pi over 2. Okay, but don't forget, I'm supposed to do this for 5 total solutions, right? So it's at this point right here that we recognize, wait a minute, I could also go 2 pi past that, or 4 pi past that, or 6 pi, or 8 pi, or 10 pi, sort of as many times as I need to past that. So in addition to this, I'm also going to have z to the 5th equals 32 cis. And then, like I said, I like to think about this as if I'm going to add 2 pi to this, I might as well make that 4 pi over 2. And so when I add 4 pi over 2 to that, I'm going to wind up with 5 pi over 2. Okay. Then I'm also going to have z to the 5th is 32 cis, and I'm going to add that 4 pi over 2 again. So now this will be 9 pi over 2. So now I've sort of got 3 of these. I'll have z to the 5th is 32 cis, adding another 4 pi, that'll be 13 pi over 2. And then finally, I'll also have z to the 5th is 32 cis, adding another 4 pi over 2 would get me to 17 pi over 2. And I think I actually forgot to mention it. What happens if you keep going? What if I did z to the 5th is 32 cis, adding another 4 pi, that would be 21 pi over 2. I'll address right at the end of this example what happens with that. So now I need to work through all 5 of these things, right? So I'm going to raise both sides of this to the 1/5 power. Right? Doing that is going to get me z1 here, the first one. Over here, it'll be 32 to the 1/5 power, and then cis 1/5 times pi over 2. Okay? That means that z1 is going to be, let's see here, the 5th root of 32, that's just 2. So 2 cis pi over 10. And we found our first of the 5th roots of 32i. I mentioned before that once you've done this once and sort of showed what your work is, it's okay for you to sort of speed a little bit more quickly through these other ones. Sorry I have all of my work really smashed in here. I hope that this is easy enough to follow. So this is now the second one, so z2, that'll be the 5th root of 32 again, so that's 2, and then cis 5 pi over 10, which would actually reduce to pi over 2. I'm just going to leave it like that. Moving on to the green one now, doing the fifth root of all of this stuff will get me z3 is 2 cis 9 pi over 10. Moving on to the red one, doing the fifth root of this will get me z4, this is the fourth one, is 2 cis 13 pi over 10. Continuing on to this first black one down here, when I raise this to the 1/5 power, again I get z5. This is supposed to be my fifth and last one, but we will sort of talk about what happens over here still. This is going to be 2 cis 17 pi over 10. And you might be wondering again, what happens when I do this one over here? Right? When I do this to the 1/5 power, I'll get z here, I'll get 2 here, I'll get cis 21 pi over 10. Why is this not a sixth solution? And the answer is, look at this argument. This argument says 21 pi over 10. But we know that if we subtract 2 pi from that, we're going to sort of get to the same angle. When I do that, that would be 20 pi over 10. This would just be pi over 10. Do you see that this angle goes back to the first one that we had? What happens is, remember that I mentioned in the previous example, all of these are sort of evenly spaced around a unit circle. So if I put these on a unit circle, right, this first one would be at pi over 10. The next one would be at 5 pi over 10, which is straight up. The next one is 9 pi over 10. The next one is 17 pi over 10. I'm sorry, 13 pi over 10. This one would be 17 pi over 10. The next one would be at 21 pi over 10, which is exactly the same thing as that one. And then this would be the 7th one, the 8th one, the 9th one, the 10th one, 11th, 12th, 13th, 14th, 15th. Like this all just keeps going around, and ultimately we really only find 5 roots for this thing. Now, you hopefully noticed at the beginning of the problem that it said, hey, write your answers in cis notation, which means it's fine to leave it here. You do not need to plug these into the calculator. If it said a plus bi and they were like this, non-unit circle values, just means you'd use the calculator to do the cosine of 17 pi over 10 and the sine of 17 pi over 10. This is definitely something that you guys can do. This last example is fairly involved, but I really, really wanted to go through it because it really shows how IB and any interesting problem writer can find ways to combine together a few things. So what we're going to be doing in this problem is we're going to be finding cube roots, and then expanding a binomial, and then solving a quadratic. And I assure you, all of these things are going to end up linking together. It ends up being a really, really, really neat thing for you to be able to see kind of right when we get to the end of it. So let's start out in part A by finding the cube roots of negative 27. So this would be z cubed equals negative 27. We know that the way that we need to do this is by converting this side into polar. So negative 27 is over there. That's an angle, an argument of pi, with a modulus of 27. So this is going to be z cubed is 27 cis pi. But remember, I'm supposed to have 3 solutions here. So I'm also going to be doing z cubed equals 27 cis 3 pi. That just comes from me doing pi plus 2 pi. And then I'm also going to do, we'll use green, I'll also do z cubed is 27 cis 5 pi. Okay. Now I'm going to follow the same process I've used for all of these other ones. I'll take this first equation and raise it to the 1/3 power. Okay. De Moivre's theorem lets me, the left side is z1. De Moivre's theorem lets me bring these things in here. So this would be 27 to the 1/3 cis 1/3 times pi. That means that z1 is 3 cis pi over 3. And the problem said that we wanted these things in the form a plus bi. So that means I'm going to go ahead and actually expand these out. I know I'm running a little low on space here, though. So this is going to be 3 cosine pi over 3 plus 3i sine pi over 3. The cosine of pi over 3 is up here. Cosine is a half. So half times 3, this is going to be 3 halves. Okay, so 3 halves plus the sine of pi over 3 is a tall positive value. So this is going to be 3 root 3 over 2i. So here I found one of my cube roots of negative 27. Let's move forward and find the other ones. Okay. This one, when I raise the whole thing to the 1/3 power, I'll get z2 is, again, bringing this in using de Moivre's theorem, 3 cis pi. Oh, and that one's actually really easy. Z2 is going to be 3 cosine pi plus 3i sine pi, but sine pi just turns into 0, and cosine pi is -1, so z2 is -3. So I found kind of like my easy, obvious cube root of negative 27. And then for this last one, there's kind of two ways that we can go about this. One of them is by doing the work and raising this to the 1/3 power. That would get me z3 is 3 cis 5 pi over 3. And then using a similar process like we did up here to expand it, we can find that z3 is 3 halves minus 3 root 3 over 2i. And I'm kind of skipping the work on that, both to save time and to show you the other sneaky way to do it. This was a real polynomial. So because it was a real polynomial, as soon as we had one root, we knew the other was going to be the conjugate of that. So it's not surprising that we would have wound up with that. So yay, we finished part A. Now part B on this problem is honestly where you might start to feel like, what? You want me to expand that? Like, what in the world does this have to do with part A? And I kind of have to like promise or assure you, IB doesn't do things for no reason. Like they're having you do this for a reason. It's going to build to something. So let's see what we can do here. Part B of this, they want me to expand 2x minus 1 cubed. All right. I want to keep all of this work here because we're going to need it, but I need some more space to work with here. This really goes back to what we learned about our binomial expansion triangle and the binomial expansion theorem. So if you build your binomial expansion triangle down to the third row here, we'll find that the row we want is 1, 3, 3, 1. So this is going to be 1 times 2x cubed plus 3 times 2x squared and the -1 to the first power. Right? Remember what happens here is that the powers on these sort of just trade off. It starts with 3 and 0, and then it goes to 2 and 1. You can sort of pause the video and think for yourself, like, what's this next term going to be? It's going to use this 3, and then it'll use 2x to the first power and -1 squared. And then one more time, pause the video or make sure you can think quickly. What's this last term going to be? It'll be a coefficient of 1. At this point, I'm not using any of the 2x terms anymore. I'm just using -1 to the third power. So when I sort of multiply this whole thing out, it's 8x cubed plus 12, oops, not plus, minus 12x squared plus 6x minus 1. So this is what 2x minus 1 cubed is. So now we move on to part C. And part C is asking us to solve the equation 8x cubed minus 12x squared plus 6x, and we're feeling really good about this, by the way, because everything's like matching up with this. It feels like part B made sense. And then it says plus 26 equals 0. And you're like, what? Like that it felt like it was so close to what we had before, but it wasn't really, But trust them, like they're doing this for a reason, right? What you need to do now is you need to go, hey, how can I rewrite this? Is there any way for me to like modify this a little bit so that it says -1 at the end? And there is, in fact. If I did 8x cubed minus 12x squared plus 6x minus 1, what would have to go next to that -1 in order for this to work out? Wouldn't this need to be a plus 27 so that these two things together would be plus 26? And then wait a minute. If I wanted to solve this thing, maybe I could like move the 27 over to the other side. I could have 8x cubed minus 12x squared plus 6x minus 1 equals -27. And right here, if you haven't seen it before, the whole problem starts to come together. And you can really see how all of these things interact with one another. What's special about this thing on the left? How can I rewrite that? How can I factor that? Didn't that thing come from 2x plus 1 cubed? I'm sorry, 2x minus 1 cubed equals -27? And then if you wanted to solve that, wouldn't you want to, like, cube root both sides? Right? If I cube rooted both sides, oh man, at that point I would need to know what all of the cube roots of 27 are. If only at some point in the past we had figured out what all 3 of the cube roots of negative 27 were. Hey, would you look at that? We did do that, right? Again, I need more space, so I got to shrink this a bit. So on the left-hand side, I've got 2x minus 1. And on the right-hand side, I've got all 3 of the different cube roots of 27. I've got the first one that I got, 3 halves plus 3 root 3 over 2i. I've got the second one that I got, 2x minus 1 equals, oh, this was the easy one. It was negative 3. And then finally, I've got, maybe I can move it up into this space. Sorry for the mess here. Maybe I can just move down this way. The last one, this like green solution, would be that 2x minus 1 has to be 3 halves minus 3 root 3 over 2i. And then for each one of these, it's just a matter of solving. For this first one, I'm going to add the 1 over. That'll get me 2x equals 5 halves plus 3 root 3 over 2i. And then I can divide through by 2. So x will be 5 fourths plus 3 root 3 over 4i. And I found one of my solutions to this equation from C. This next one is even easier. When I add this 1 over, I'm going to get 2x equals negative 2. So x is negative 1. Okay, yay. And then for this final one, this last green one, I'm following the same steps that I did over here. So first adding the 1, this will get me 5 fourths minus 3 root 3 over 2i, and then, 5 halves. And then when I divide by 2, I'll get the 5 fourths minus 3 root 3 over 4i. I mean, and I did warn us, this was going to be a really involved problem. This is the kind of thing that might be a multi-part, like blue or even maybe red problem. Being able to see and pull all of these things together is a challenging thing. So I hope you made through it, all of that. If you have any questions, write them down and ask me. Put them in the comment when you submit your assignment on the Google Classroom so I can respond to it. And I wish you best of luck in your assignment and in your practice.